This video is not an introductory video on resonances in dynamic systems. It is both a reminder of things seen in previous courses or in previous lectures from this course, and an introduction to things that will be seen in more detail in future courses. It's a sort of wrap-up on the essential concepts of the analysis of resonance systems. We are going to look at both mechanical systems and acoustical systems, and this is an important video making the link between the two parts of this course. So let's start with the most simple system of all that you've seen before. It's just a single degree of freedom system, undamped. So we have just a mass m resting on a spring of stiffness K connected to the ground. It is excited by a force F, and we want to know what is the displacement U. I'm going to use a convention that I'm using throughout the book. When I use capital letters, I mean the spectrum. So capital U is the spectrum of the signal UT, which is written in lowercase. So lowercase is for signals and uppercase is for spectra. So we go from one to the other using the Fourier transform or the inverse Fourier transform. If we apply the very basic principle of mechanics to the system, we see that we can describe the displacement by a differential equation, which is just that mass times acceleration plus the stiffness constant times the displacement is equal to the applied force. And if we translate that to the frequency domain, remembering that a first derivative gives an I omega term, a factor in the frequency domain, and a second derivative gives a minus omega square factor, we see that in the frequency domain this equation is just k minus omega square m times the spectrum of displacement is equal to the force spectrum. And so in the frequency domain, the differential equation has become an algebraic equation that we can very easily solve, and so the spectrum of displacement capital U omega is equal to the spectrum of force capital F omega divided by a term which depends on the two main physical constants of the system, K and M, but also on the pulsation omega, which as you remember is 2 pi times the frequency. And immediately when you look at such an expression, you realize that there is one very special value of omega, which is the value for which k minus omega square m is equal to 0. So when omega is equal to plus or minus square root of k over m, well, we see that the displacement goes to infinity. And that gives us a first definition of resonance frequencies or resonance pulsations. A resonance frequency is a frequency at which the response of the system becomes infinite. Of course, we're talking about undamped system. You see that omega can be equal to plus or minus square root of k over m. I will disregard that plus or minus sign because a system that vibrates at 100 Hertz or at minus 100 Hertz is exactly the same thing. There is just a phase difference between the two motions, 180 degree phase difference between the two motions. So we have a first definition of resonance frequencies, which is that a resonance frequency is a frequency at which the response of the system is infinite. But there is another way to look at resonances. Consider exactly the same system, but this time assume that there is no force. The equation just becomes m times acceleration plus k times displacement is equal to 0. And in the frequency domain, it gives k minus omega square m times the displacement spectrum is equal to 0. And we see that this equation can have two types of solution. Either we consider that u omega is equal to 0, meaning that the mass is not moving, is perfectly at rest. This is possible provided that the initial condition to the equations are consistent with that, so that if it's not moving and there is no force, then it cannot start moving and it stays still. But then there is another solution. If omega is equal to square root of k over m, we see that u can be anything different from 0 possibly. And so that gives us a different look at resonance frequencies, which is that a dynamic system on which no force is acting is either static or vibrates at its resonance frequency 1 over 2 pi square root of k over m. And there is a third way to look at resonances. Let's look again at the equation for the single degree of freedom system. N times acceleration plus k times displacement is equal to f in the time domain. And let's multiply that by u dot, so the velocity. Well, you see that m times u double dot times u dot can be written as the time derivative of mu dot square divided by 2. Indeed, the derivative of mu dot square is 2mu dot u double dot, so the two cancels each other. And same thing for the second term, ku u dot is just the derivative with respect to time of ku squared divided by 2. And so you see that we can write this equation in another way, saying that the derivative with respect to time of mu dot squared divided by 2, which is the kinetic energy, a function of time, how kinetic energy changes with time, plus ku squared divided by 2, which is the elastic energy stored in the spring. Well, the derivative of the sum of these two terms is equal to the power provided by the external force. And so we have a power balance in this equation, which says that the power provided by the external force is just there to produce the variation of kinetic plus potential energy in the system. So let's look at kinetic energy and potential energy for a harmonic excitation, and we assume that the system is in regime, so we don't look here at the transient aspects. And let's look at that at three resonances, three frequencies: before the resonance, after the resonance, and at the resonance. Here we are before the resonance to start with. And the dotted curve gives us the potential energy, the dashed curve gives us the potential energy, the dotted curve gives us the kinetic energy, and we just see that kinetic energy and potential energy changes with time. When the mass is at its rest position, the potential energy is 0, then the potential energy is maximum, 0 again, maximum, 0 again, and so on twice per cycle. Same for the kinetic energy. The velocity is maximum at the rest position, then becomes 0, maximum again, 0, and so on and so forth. But what you see, let's look at two instances. First, the green points. At the green points, we see that the potential energy is 0, the kinetic energy is maximum, and at the blue dots, we have 1/4 of a cycle later, we have the opposite, the kinetic energy is 0 and the potential energy is maximum. But what we see is that the maximum potential energy, the maximum energy stored in the spring during the cycle is larger at a frequency that is before the resonance, larger than the maximum kinetic energy. And so there is too much energy stored in the spring than is necessary to accelerate the mass to the required velocity. And so the force needs to provide work to brake, to reduce the speed or reduce the acceleration of the mass, but then also to provide the additional compression in the spring. And so there is actual power provided by the force, and there is an exchange between the system and its environment. If we look at the same thing after the resonance, it's just the opposite. You see now that the maximum kinetic energy is larger than the maximum potential energy, and so once again, to handle that difference, there is a power flux. The external force needs to provide or receive power from the system. And as you may guess, at the resonance we are just at the transition where the maximum kinetic energy is equal to the maximum potential energy. And so the energy stored in the spring is just sufficient to produce the right acceleration, and vice versa, the kinetic energy is just sufficient to compress the spring as required. And so the force does not need to provide any power to the system to get it moving, and that's also a new definition of resonance. At the resonance, the potential energy stored in the spring is just that required to accelerate the mass. The external force does not need to provide any work. There is no power flow between the system and its environment. We have looked so far at conservative systems. What happens when we look at a damped system, which is more realistic, of course? Well, we have to add to the equation a term that is proportional to the velocity, because we want to handle viscous forces in the system. And in the frequency domain, that translates into an additional term with an imaginary component. So that if you consider a damped system with a dashpot, a dissipative component, well, the displacement is equal to the force divided by a complex frequency-dependent quantity. And you see that as soon as there is any damping, when d is different from 0, well, you never divide the force by something that becomes equal to 0. So, strictly speaking, only conservative systems do resonate. There is no frequency at which the system responds in an infinite way. And of course, the response of the damped system is still very high near the resonance frequency of the equivalent undamped system. And so resonances are important in damped system, but strictly speaking, the frequency, the response never goes to infinity. And the external force, the power provided to the system by the external force never becomes exactly 0, because even at or close to the resonance, the environment still has to provide at least some power, if only to compensate for the dissipation in the dashpots.